Hi everyone, my name is Jimmy Crawford. I'm a PhD student in Dr. Moises Carreon's lab, and today I'm going to be walking you through our interactive poster presentation. And this poster should be available online for your viewing. So what we're starting out with here is just the three pillars of our lab. And our lab group is focused on three key areas. One is synthesis of solid materials. Two is the application of those materials to potential membrane separations. And three is application of those materials to heterogeneous catalysis. So walking through these three pillars one at a time, starting out with the porous materials we refer to as sorbents, you can see an example of a synthesized sorbent material here with the SEM image, and you can see a beautiful crystalline structure of one of our favorite materials, CC3. So CC3 is a type of material that's made via microwave synthesis. And so we have many different pathways to synthesizing materials in our lab, and one of them is microwave synthesis. And this is not exactly your typical piece of equipment that you would find in your kitchen, but rather something that causes the nucleation of fine crystallites in solution. So another example of material that we synthesize in our lab are metal organic frameworks. And so these include things like HCUST, which is really well known in the literature, and other types of metal organic frameworks like ZIFs. Another synthesis route that we've reported in our lab is evaporative self-assembly. And this is when you essentially have a solution with the particular components required to start forming a solid, but they're highly dilute. And so as the solution evaporates, the precursors become more and more concentrated and eventually nucleate and form very fine crystals. So the SEM image there is of, again, CC3 and some different nucleation sites you can see caused by this evaporative self-assembly. Another synthesis technique we use is hydrothermal synthesis, and this is the addition of multiple precursors into a pressure vessel. And so they'll be added in controlled amounts, sealed off in either an inert atmosphere or just an air atmosphere, and then they'll be placed in a furnace and be heated up to result in the nucleation of something like a zeolite. So typically zeolites are formed through hydrothermal synthesis, and some exemplary zeolites are listed here, as well as an image of zeolite Y, which is a relatively large pore zeolite with industrial applications. So in theory, once you have your material synthesized, you can apply it to a realistic real-world problem. One example of that would be the separation of light gases using solid membranes. And so this is something that our lab group historically has done a lot of work on. So gas separations of interest could include anything from CO2 and methane from a natural gas reserve, or no inert gases like krypton and xenon that could be industrial waste produced from nuclear power plants. So there are lots of different examples of gas separations that would be of interest. And so there are three fundamental areas of gas separation that our lab has worked really heavily on. And these three are starting with the first, molecular sieving. And this is where you have a fine membrane layer, for example, a zeolite that separates two gases depending on the pore size of the zeolite. So say your zeolite is 0.2 nanometers and your two gases sizes are 0.3 and 0.1. Obviously, the gas with 0.1 nanometer diameter would pass through where the other would be rejected. Another fundamental area in zeolite separations is the difference in diffusivities. And this is some data from previous work on the separation of helium from methane. And here you can see that the two gases have far different diffusion coefficients in the zeolite membrane of interest, allowing helium to pass more rapidly than methane. And there's a couple of different membranes that were synthesized in this experiment, all relatively similar results, showing that helium was passing faster than methane. A final important fundamental for the separation of gases using membranes is competitive adsorption. So this is how strongly one gas adsorbs to the separating layer compared to the other. And this information can be elucidated by collecting isothermal data using your original crystalline material and comparing the adsorption affinity of one gas versus another. So the third key area in our research is catalysis. So we can synthesize these porous materials using rational design and apply them to realistic reactions that are of major urgency in our developing society. So an example of this would be the production of biofuel. So using biomass and producing a minimal amount of CO2 in the production of a liquid fuel. Another would be utilizing carbon dioxide, either in forming methanol or forming other longer alkane products. And so there's a number of valuable heterogeneous catalysis reactions that we're interested in studying, and they can be studied in batch or continuous reactor phases. So here's an example of one of the materials we synthesized, which was a zeolite bead with a metal organic framework layer on the outside. And this material had high performance for the conversion of a fatty acid into an alkane liquid fuel. And so the key pillars of catalysis are first characterizing the material physically, and that includes pore size, pore geometry, and crystallinity, which can be elucidated through isotherms and through diffraction experiments. The next is the chemical characterization, which involves elucidating the active sites, the amount of metal, the dispersity of the metal, perhaps the oxidative state of your metallic catalyst on its support. And here's an example of TEM showing the two different chemicals that are at play, which were nickel supported on silica. So you can see that the nickel is finely dispersed across the surface from the TEM study. And then finally, once the material is well characterized, we can subject it to catalytic tests. So this is some data pulled from some of my work, which is showing, with respect to time, the yield or conversion of acetic acid in producing various products, including methane, ethane, and methanol. And key concepts here are conversion, selectivity, and yield, which we can all get from the online mass spec or FID detectors that we have in our lab. So that's just a brief overview of the research we do in the Carreon lab. Generally speaking, it's the synthesis of some kind of a porous material and its application to some kind of an industrial problem. And we're happy to be funded by the DOE, ARPA-E, and NSF. And we thank them for their continued support. Thank you for listening. And if you have further questions, feel free to visit our website, carreonlab.mines.edu.